Shall I start the class? Once again, I am reminding more. Everyone, please log in with your roll number and section. Otherwise, it will be treated as absent. We won't give you attendance. Is my voice audible? Okay. What we taught in the last class? In the last class, we have seen what is a instruction cycle. What are the different phases involved in execution of an instruction we have seen, and we already saw what are different register reference instructions along with their register transfer languages. Right? Now we'll see memory reference instructions. What are the memory reference instructions we have seen in the previous classes? But in today's class, we'll see what are the corresponding register transfer languages for the memory reference instructions and in which time cycle they'll be executed. Clear? Let us see. I already explained the first two instructions. What are those? Add and. Add instruction as well as AND instruction I have already explained. What do you mean by AND instruction? AND instruction. AND instruction will perform AND operation between the data present in the accumulator and the data present in a memory location specified in this address. Specified by this 0 to 11 bits address, right? And we have already seen what is the corresponding register transfer language. Second memory reference instruction is add. How to perform add? First data is get the data from the accumulator. To that accumulator data, we need to add the data present in a memory location. And in which memory location the data is present, that address will be given by the 0 to 11 bits of your IR register. So 0 to 11 bits always specifies the address for memory reference instructions in this 16 bits of IR register. Clear? These two we have discussed in the previous class. Now the third instruction is load instruction. What is to be loaded? Where it is to be loaded. Load the content of the memory into the accumulator. Right? So here the 0 to 11 bit specifies the address. Go to that memory location, whatever is there in the address register, those 0 to 11 bits, go to that memory location, retrieve the data from the memory and place it into the DR. Place it into DR. Now the question is, what is this LDA operation? LDA is transfer the memory content into the accumulator. Okay? So when you observe these register transfers, first what I am doing, I am going to that corresponding memory location. From there I am retrieving the data and I am placing it into the data register. In the second clock cycle, that is in the next clock cycle, from the data register, we are moving the data into the accumulator. Now the question is, why I am not moving the data directly from this memory allocation to the accumulator? Why we are not moving the data directly from the memory location to the accumulator? If you remember the common bus system, you will answer this. Any answer? Any answer? Why the data is not moved directly? Yes, because from the common bus system, when you see the common bus system, there you don't have an input line from the common bus to the accumulator. From the accumulator, you have an output line, but you don't have an input line to the accumulator. Accumulator will get the data from the data register. That is the reason You cannot directly move the content direct from memory to the accumulator. So in between what I am using, I have to place it into the data register. From the data register, you can move it to accumulator. Now this instruction is done. Whenever one instruction execution is done, you can make the sequence counter to 0. So made SC as 0. That is the third instruction. Move on to the next instruction. Fourth one, STA, store the accumulator. Load the accumulator means load the content from memory to accumulator. Store the accumulator is store the content of the accumulator into the memory, the reverse of LDA. So you know that content present in the accumulator. This content I need to store it into the memory. Into the memory, in which location I have to store? That address will be specified by the 0 to 11 bits of your instruction register, that is your AR. So whatever the address is specified, go to that memory location and place the content of AC into that location. Instruction is done. Made the sequence counter to 0. When you observe this instruction with the previous one, first instruction is done in 2 clock cycles, and in the same way, second instruction also requires 2 clock cycles, third one also requires 2 clock cycle, but this STA will happen only in 1 clock cycle. Only in one timing cycle, STA instruction will be executed. Now move on to the next one, BUN instruction. Branch unconditionally. Branch unconditionally. Right? So generally your program will contain the instructions to be executed, the sequence of instructions to be executed. 1, 2, 3, so on up to like 10, something like that. If the program contains 10 number of instruction. In case of branch unconditionally, you can jump from one instruction to the another instruction which is not there in the sequence. That is what BUN instruction means, right? So you can change the sequence of the instructions to be executed when you encounter this BUN instruction. So try to write the way register transfer language. So whatever where you want to jump, that address will be specified in AR register. 1, 2, 3. Assume that I am at instruction 3. Presently I am executing instruction 3. After 3, which is there in the sequence, fourth instruction will be there in the sequence. But when you encounter a BUN instruction, instead of 4, you can jump to another instruction, something like 10. Where you want to jump, that will be specified into which address or into which instruction you have to execute, and where that instruction is present in the memory location, that address will be specified in the AR register. 1 second. That address will be there in AR register, right? Always your program counter holds the address of the next instruction, right? As you are jumping to another instruction which is not seen the sequence, and what is that address? Where that address is present? That is present in your AR register. So move the content of AR into the program counter, because always we'll get the data, always we'll get the next instruction to be executed, address of the next instruction from the PC. So what is the next instruction to be executed? That address will be stored into your PC. That is your BUN instruction mean. When this instruction execution is done, you can make the sequence counter to 0. This also happens only in 1 clock cycle. And the next one is BSA instruction. Branch and save instruction. 1 second. Why it is not moving? 1 second, ma. Sixth one is branch, BSA, branch and save the return address. In case of BUN, in what we are doing, from one instruction, you are jumping into the another instruction unconditionally. And once that instruction execution is done, where you are supposed to come back, that we are not saving. That return address you are not specifying. It is something like a function calling, ma. right? So here in case of what you are doing BSA, we are jumping to the instruction which is not in the sequence, and once that instruction execution is done where you are supposed to come back, that address needs to be stored before you jump. The address of return needs to be stored before you make a jump, right? Before I explain this, let us see one example. Before we see the register transfer language for BSA instruction, let us see the example. Assume that I am executing the instruction which is present at location 20. Initially, my program counter value is 20. Then the control will go to 20th location in the memory, right? What is there here? Here you have an instruction which contains the type of instruction as BSA, which is BSA instruction. Branch and save the return address, right? Now, here whenever you whenever you retrieve this instruction, immediately your program counter value will be incremented. So your PC now it becomes 21. That means after executing this instruction present at 20th location, you have to execute the next instruction which is at location 21. As this is BSA instruction, so you need to save the return address at location 135. The return address needs to be stored at location, memory location 135. After that, you will have whatever the subroutine you need to perform, that will be executed. Once this is done, where you are supposed to come back, that address will be stored at 135 location, right? So whenever you are executing the 20th instruction, assume that this is not a BSA instruction. Assume that this is something like add instruction or whatever the other than BUN and BSA instruction it is. Then what you will execute? You will execute the immediate instruction in the sequence, that is 21. But here what you are doing, instead of executing 21, after this you are jumping to the location 135, and here you don't have any instruction. What you are writing here, what is present in 135, after executing this subroutine, where you are supposed to come back. That means after completing this subroutine, you have to come back to the location 21. That address, return address, I am saving at 135th location, right? So next, at 135th location, you are saving the return address. From the next location, you will be having your subroutine to be executed, right? So from 136th location, you will be having your subroutine. Now, as this subroutine is done, you have completed the execution of this. Next, what is the next instruction you have encountered? 1 BUN 135. What does the meaning of 1 here? This represents the ith bit. If your ith bit value is equal to 1, it represents indirect address. That means whatever the instruction you want to execute after this instruction, the address of that will be present at location 135. Is it clear? If it is a direct instruction, then here you will have 21. Here, instead of 135, you will have the address as that 21. That means at 21st location, you will have the instruction to be executed, right? As it is indirect, so 135 is the address of the address. So go back to 135th location. Here you will have the address of the next instruction to be executed, right? So what is the address? 21. So go back to 21st location. Here you will have the next instruction to be executed. Is it clear? Now we'll see the corresponding register transfer language. First, what is the first step you are doing? You need to save the return address. What is the return address? Your return address is 21. That means after executing 20, as it is BSA instruction, the subroutine will be executed, right? After this, you need to come back to 21st. So you need to come back to 21st. That program counter value you are storing at one location, address AR. You are storing at AR. What is present in AR? This is your 16 bits of your instruction, IR register. So this specifies AR. What is the value of AR? AR is 135. So the address of the next instruction, that your PC value, that return address you are storing at 135. So PC value is stored at 135, M of 135, memory location 135. So 21 value is stored at memory location 135, right? Whatever we have, that is what I have done here. 21, the return address you have stored at 135 location. Next step, what is the next step? Increment AR, because the subroutine starts from here 136. So increment your AR. AR equal to AR plus 1. Always you will get the address of the next instruction from the program counter only, right? Therefore, this modified, updated AR value should be transferred to PC. So, control will go to PC as the value of PC is 136 now. Now the value of PC becomes 136. So what is there at 136, that will be executed. And once the execution is done, made the sequence counter to 0. Clear? BSA, branch, jump to the next instruction which is not in the sequence, and at the same time save the return address. Once that instruction execution is done, where you are supposed to come back, that address needs to be saved. Clear? Next. And the last memory reference instruction is ISZ, increment and skip if 0. Increment and skip the next instruction if 0. What is to be incremented and which is 0? When do you skip the next instruction? Increment the content present in the memory word. Increment the content of the memory word, and after incrementing, if that memory word value is 0, then you need to skip the next instruction, that is ISZ. Let us see the RTL. So address register will contain the address of the memory location. Which memory location data needs to be incremented? First, what you are doing is go to that memory location. Go to that memory location. Whatever the data is present there, move the data into your data register. Move the data from the memory to DR. Next, DR will be incremented by 1 because you need to increment the word specified by the address. Whatever is present in that address, that data needs to be incremented. You cannot increment the memory, the data present inside the memory location directly. Directly you cannot apply increment operation to that word which is present in the memory. That is the reason, first what you need to do is retrieve the data from the corresponding location, place it into the data register. After that, apply increment operation, place that modified data into the memory location. Get the data, place it in DR, apply increment, place the updated value back into the same location. Now, after incrementing, if that memory value, that memory word becomes 0, why I have written DR equal to 0? Because the updated value you are storing it into DR. From DR you are placing into the memory location. So if that DR value becomes 0, then you need to skip the next instruction. So PC value should be updated. The instruction, ISZ instruction is done. Make the sequence counter to 0. Who is writing on the screen, ma? Will mark absent for you. 55E. Is that you writing on the screen? If you do the same again, we'll mark absent for you for whole week. So these are all the memory reference instructions, ma. And what is the corresponding what we call register transfer languages. So as AND operation is executed in 2 clock cycle, so these are the two register RTS for AND. Similarly, whatever I have explained here, I have written in the form of a chart. In the form of this chart, I have written all the memory reference instructions. Add, which again executed in 2 clock cycles. Load, 2. Store instruction requires only 1 clock cycle. Next, BUN, BSA, ISZ. These are the 7 memory reference instruction. Clear? Next category. Next, the third one is IO instruction. Reference instructions are memory reference instruction, register reference instructions, and IO instruction. These are the 3 categories of instructions. Before we discuss about IO instructions, first the input output system of a computer system will work. How the data will be taken from the input device, when the data will be placed. For purpose to do this, to take the input and to place the data onto the output device, you require 2 register, INPR register and OUTR register, input register and output register. Input and output register. So, what is the size of INPR and OUTR? Input register size and OUTR register size. The size of these two is 8 bits. First, what happens is, first you need to get the input from the input device, then you can place the data onto the output device. Let us suppose I am considering keyboard as my input device. So these two are input and output devices. To transfer the data from input device into the your output device, you require an interface. So to transfer the data from input device to INPR register. Why? Because INPR is the one which holds the input characters. Whatever is coming from the input device, those data, the data will be placing into INPR register. Through the interface, transmitter interface, the data given by the input device, here in case of keyboard, the data given by the keyboard is placed into INPR register through this interface, through this transmitter interface. Right? Now here you require 2 flag values, 2 flip-flops, FGI and FGO, to move the data, to place the data into INPR register and to move the data from INPR. Similarly, when to place the data into OUTR register, when to move the data from OUTR register, that is decided by using 2 flip-flops, FGI and FGO. Flag input, flag output. Flag input and flag output. So initially FGI value is set to 0. Initially FGI value is set to 0. Whenever the value of FGI is 0, the data given by the input device, that is data from keyboard, is placed into INPR register. Whenever the data is placed in INPR register, after that FGI is set to 1. When FGI is 0, data from the input device can be placed into INPR register. Once the data is placed, INPR holds the input character, FGI is set to 1. Whenever FGI is set to 1, you can move the data from INPR register to the accumulator. Right? At the same time, while moving the data from INPR to accumulator, if you are getting any data from the keyboard, those data will not be stored or will not be accepted by INPR. So your transmitter interface will maintain a queue for incoming characters, for incoming input characters. Right? So Once the data is moved from IMPR to accumulator, FGI will become 0 again. Whenever FGI is 0, you can accept the input character from the keyboard. Whenever one input character is placed in IMPR, immediately FGI is set to 1. If it is 1, IMPR will not accept the data or will not store the input characters. Now the data from IMPR is moved to accumulator. Now here you have one more flag for outputting the data, that is FGO. Initially, flag output. Initially, FGO is set to 1. Yes, FGI is initially set to 0. FGO, it is initially set to 1. Whenever FGO is set to 1, it will accept the output character. Your OUTR register will accept the output character. So, from the accumulator, the data is accepted by the OUTR register. Once the data is placed in OUTR register, FGO is set to 0. Initially, it is 1. So, OUTR is ready to accept the data. Once the data from AC is accepted, it made FGI value is set to 0. That means OUTR is in the process of transferring the data into the output device. FGO equal to 0 means the output process has not yet completed. So whenever FGO is 0, OUTR register can place the data onto the output device, something like printer, through a receiver transfer. Once this transfer is done, FGO value can be set to 1. Whenever FGO is 1, OUTR register can accept the data from the accumulator. Clear? This is the working of IO system. Right? Using a flag input and flag output flip-flops, the data can be accepted by the input device to IMPR. From OUTR register, it can be placed on any output device. Here I have written whatever I have explained here. You please go through these slides. Next, we will see what are the different types of IO instructions. Different types of IO instruction. Now tell me what should be. In the previous class, I explained that based on the decoded value D7, you will decide whether it is a register reference, memory reference, or IO instruction. Right? If the decoded value D7 is equal to 1, then it can be either register or IO instruction. If it is 0, then it will be memory reference instruction. Right? So first condition is D7 value should be equal to 1. Now, when it is 1, it can be either register or IO. How to decide whether it is register or IO? Based on the ith bit. For register reference value, ith bit value should be equal to 0. That is the reason for register reference we'll write D7 I bar T3. For IO instructions, if the 15th bit of your IR register is 1, then it will be your IO instruction. That is I. Your I should be equal to 1. So, it will be executed at third clock cycle T3. And the value of D7 should be equal to 1 and 1 should be equal to 1. So, this is common for all the IO instructions. What type of IO instruction it is, that is decided by the bit value. Okay? So 0 to 11 bits of your IR register specifies the type of the IO instruction. We know that we have 6 IO instructions. 6 IO instruction. So only the bit values from 11 to 6 will specify what type of instruction it is. Remaining 5 to 0 bits of your IR will be 0 only. Now see what are those instructions. What are the 6 IO instruction. First one is INP instruction. When this INP instruction is executed, you just remember what we have taught in the two classes back. At the time of register reference instructions, I explained register reference IO instructions. I explained the format of your IR, the format of your instruction register. So the value should be the opcode and ith bit value should be equal to 1111 for IO instruction. By changing the 0 to 11 bits, you can get different value. So if it is PB11, that means if the 11th bit is equal to 1, 11th bit is 1 means remaining bits 10 to 02 bits are equal to 0. 10 to 02 bits are 0. If it is PB11, then INP instruction is executed. What is INP instruction? Input the character to the accumulator. Input the character to accumulator. So from IMPR, you send the data to the accumulator. Accumulator 0 to 7 bits. Why I have specified this 0 to 7? Why we have specified 0 to 7 here? Why we can't write AC tends to INPR? Because size of INPR register is 8 bits, but the size of AC is 16 bits. So into 0 to 7 bits, you need to move the content of IMPR. So IMPR content will be placed in 0 to 7 bits of your accumulator, right? Next, at the same time, what we have to do, when you can perform this transfer of data from INPR to accumulator, when FGI value equal to 1. When FGI equal to 1, you can perform. Once this transfer is done, you can make this FGI equal to 0. So this is FGI becomes 0. Next, OUT instruction is executed at PB10. When the 10th bit of your IR register is 1, then output a character from the accumulator. Output character from the accumulator is executed. How to write this? Whatever is present in your OUTR register, as the size of OUTR is also 8 bit, but the size of accumulator is not 8. So in the accumulator, use 0 to 7 bits for placing the data of OUTR. So from these 0 to 7 bits of your accumulator are placed into your OUTR register. When can we perform the transfer of the data from accumulator to the OUTR register? When can we perform transfer of data from accumulator to OUTR? When do we perform? Whenever, yes, when FGO is 1, then only you can perform, right? So once this transfer is done, you can make FGO to 0. Right? That is output the character from the accumulator. Next is SKI instruction. When the 9, it is PB9. When the 9th bit value is 1, then SKI is instruction is executed. What is SKI? Skip the next instruction if the input flag is on. That means what is input flag? FGI is input flag. If the value of FGI is 1, then skip the next instruction. So increment the program counter. Similarly, SKO, it is executed when the 8th bit is 1, PB8. Skip the next instruction on output flag. Output flag is your FGO. When the output flag is 1, skip the next instruction. So, change PC to PC plus 1. And the last two are PB7, which is ION. IEN set to 1. IEN is a flip-flop used to know whether interrupt has occurred or not. So IEN is set to 1 means interrupt enabled on. Interrupt is enabled. Interrupt has occurred. IOF, it is executed at PB6. When the 6th bit of IR is 1, IOF is executed. Interrupt enable off. IEN is set to 0 means interrupt enable off. Now we'll see what is this interrupt. Okay? These are the input output instruction. So in these IO instructions, interrupt is enabled and interrupt is switched off for PB7 and PB6. So we'll see what is an interrupt is. Generally, interrupt means what? Abruption. While executing the program, in the middle of program execution, if any IO operation is occurred, then we can say that it is an interrupt. We are in the sequence of executing the program. Some sequence you are following, but in the middle, if an IO instruction is done, then what you have to do? You need to either you have to accept the data if it is input operation, or if it is an output operation, you need to output the character to the output device by passing the next instructions which are there in the sequence. That is known as interruption. But these interruptions are not known before you start the program. You may get a question, why to stop the execution of the program in the middle when there is an interrupt? Because you don't know when that interruption will happen, when the user will enter the key, when the user will give the input, that you don't know. So IO operations all are asynchronous operation. That is the reason in the middle of executing the program, if an interrupt is occurred, if any IO operation has occurred, then you have to stop the program in the middle and you have to go to that interrupt. That interrupt has to be serviced. This is something like your BSA instruction. Interrupt is just equivalent to BSA instruction. What is BSA instruction? Branch and save the return address. You are executing some sequence, you are following some sequence for execution, but you are in the middle of execution, you are branching from one location to the another location. In the same way, here in case of interrupt also, while executing the program, if an interrupt is occurred, you need to go back to interrupt service routine. That interrupt has to be serviced first, then only you can come back to the return address. You can come back to the previous instruction. Clear? That is what interruption is. Let us see how this interruption is done. So to decide this, you require a flip-flop known as R. R is the flip-flop which is used to know whether interrupt has occurred or not. If the flip-flop always holds one bit, either 0 or 1. So if the value of this R flip-flop is 0, it means that there is no interrupt. It is an instruction cycle. Interrupt is not there means you can proceed with normal execution of the instruction. So you know how to execute an instruction. What are the different phases involved in an instruction? What are those? Fetch, decode, get the effective address if it is an indirect address. If it is a direct address, third step can be skipped. Third phase can be skipped. And the last one is execute your instruction. So if the value of R is 0, then it will be your instruction cycle. You know what to do for an instruction. Fetch the instruction, decode the instruction. Decoding means decide what is the operation to be performed. Fetch and decode. After that, you can proceed with the execution of the instruction. Now, at the time when you are decoding the instruction, at that time, if you identify this IEN flip-flop value as 1, whenever you are decoding your instruction, you need to check the value of IEN flag. Interrupt enabled. Interrupt enabled. If the value of IEN flip-flop, if it is 0, it means that there is no interrupt. There is no interrupt. But if the value of IEN is 1, that means interrupt has occurred. Interrupt occurred means IO operation has been occurred. IO means input output. That means that interrupt can be either an input interrupt or it can be an output interrupt. That is again decided whether it is input interrupt or it is output interrupt. That should be decided. Okay? So whenever IEN value equal to 1, you should decide whether input or output. Check the value of FGI, flag input. If the FGI value is equal to 1, it is an input interrupt. Input interrupt. Next, if it is 0, it may be the output interrupt. So check the value of FGO. Check the value of FGO. So if the value of FGO is 1, it will be your output interrupt. Whenever interrupt is occurred, what you have to do? Thus, you need to set the value of R to 1 because R is the flip-flop will decide whether interrupt is there in the system or not. So, one second. So, whenever we encounter either an input interrupt or an output interrupt, you should make the value of R to 1. Whenever R is equal to 1, you would come to know that interrupt has occurred. Now you should know what is to be done when interrupt is occurred. I told you that interrupt is just equivalent to your BSA instruction, branch and save the return address. In case of BSA, what you are doing, you are branching to some location, you are branching to a specified location and you are saving the return address which is specified. The return address is also specified in case of BSA. But here, in case of an interrupt, the return address is always 0. The return address is always 0 in case of interrupt cycle. Right? Store the return address into the 0th location. Where the return address present, always the return address. Return address means the next instruction to be executed. Once you branch to some address, where you are supposed to come back, where you are supposed to return, right? Always that is what is the next instruction you have to execute. That is always present in your PC. Store that return address where you have to store it at 0. This 0 is common for all interrupts. Whenever an interrupt is occurred, always the return address will be 0. But in case of BSA, there the return address is what? The return address is 135. Whatever the example I explained, there I have considered the return address as 135. That means at 135th location, I have stored the address of the next instruction to be executed. Right? So here PC equal to whatever is there in the PC, that should be placed in M of 0, 0th location. Next, what you have to do is increment your PC value, right? Whatever is there in PC, that you are placing into 0th location. So the next PC value will be present at first location. So move on to jump to location 1. Once that interrupt is serviced, you can make IEN to 0 as well as R to 0. That means interrupt has been serviced. Interrupt is serviced. Let us see the corresponding register transfer languages, right? So when this interrupt is occurred, whenever the value of R is set to 1, right? So if the value of IEN equal to 1 and along with this IEN, either FGI or FGO should be equal to 1, then only R will be set to 1. See here, ma. Whenever I equal to 1, either this or this should be 1, then only you need to set the value of R to 1. That is what I have written here. IEN and FGY or FGO. Either one of flag should be equal to 1. Then set R equal to 1. Here at T0th second, you will fetch the instruction. At T1 second, you will perform decoding. At T2, you will perform execution. Right? So when you see that instruction cycle, which is there in previous slide, previous classes slide. So there we'll see what we are doing at T0 at the second, what you will do at T1 second, and what you will do at T2 second. So if the clock cycle is T0 or T1 or T2, there you will perform fetching and decoding of the instruction, right? But interrupt is occurred. At that time, interrupt will not be occurred. When that interrupt is occurred, Once this fetching and decoding is done, after that only this interrupt is occurred. That means interrupt may start at from the clock cycle T3, right? So it should not be done at T0, it should not be done at T1, and it should not be done at T2, right? That is the reason it is T0 bar, T1 bar, T2 bar, and IEN should be equal to 1, or either FGI or FGO equal to 1. Then set R equal to 1. Before we see these RTLs for the interrupt cycles, let us see the example. Then I will explain this RTL statement. See here, this is my memory. This is your main memory. This is 0th location, first location, and the current program. Your current program is at 255th location. Your current instruction is whatever the instruction you are executing now, that is there at 255th location. When you are executing, the current one is 255. What is the next one to be executed? It is obviously 256, right? So initially the PC value equal to 256, right? Now where the input output operations are executed, IO instructions were executed at 1120. Always the 0th location is to be utilized for return address, to store the return address. Therefore, here at 0th location, you don't have anything. Now, at first location, you will have the interrupt instruction, means where you are supposed to jump. The branch unconditionally, BUN instruction will be there at first location. So I am executing 255. Presently I am executing 255. While executing the instruction present at 255th location, if you encounter an interrupt, if there occurs an interrupt, then what you have to do? You need to jump to that interrupt. And the return address. What is the return address? Once that interrupt is solved, where you are supposed to come back? After 255, it is 256. So this return address you need to store at 0th location. This is fixed for all interrupts. If it is BSA, that return address will be specified for different instruction. That will be different for different instruction. But for interrupts, it is 0. Right? So the address of 256 is stored at the address of 256 is stored at 0th location. Right? Next, what you have to do? See here. So the address, what is your AR? Your return address. Where you are supposed to return? The return address is 0. So that 0 should be stored at AR register. Next, what is there in PC? Your PC contains the address of the next instruction to be executed. That I am storing into a temporary register. That will be storing into a temporary register. And now what is there in TR? Your 256 is there in TR. Right? 256 is there in TR. That 256 where you are supposed to store the value of 256, I need to store at M of 0. What is 0? 0 is assigned, or 0 is assigned for AR, address register. So this 256 has to be stored into M of 0, your M of AR, right? Next, your PC becomes 0. Now your PC becomes 0. Whenever you store this 256 in 0th location, this is the current instruction to be executed. Your PC is 0. Next, what you are doing is, as you are storing the return address at 0th location, so the branch instruction, the interrupt instruction, where you are supposed to service the interrupt, that will be stored at first location. Right? That will be always stored at first location. Right? So increment your PC to PC plus 1. Now your PC becomes 1. PC value becomes 1. What is the instruction present first location? As it is a direct instruction, and it is of branch BUN instruction. The type is BUN, branch unconditionally. Where you are supposed to branch, you have to branch to location 1120. So the control will come to this location. What is there here at 1120? What you have? You have an IO instruction to be executed. Once this IO instruction is done, your interrupt has been serviced. Whenever your interrupt is serviced, you can make the value of R to 0 and IEN to 0, because once this interrupt is serviced, make IEN to 0 as well as R to 0. Right? Next, what is the next instruction after this IO? 1. That means it is an indirect instruction. Indirect instruction. So BUN, the type is BUN. Branch to the location 0. In 0th location, you don't have the effective address. 0th location. In the 0th location, you will have the address of address. So go to the location 0. Here, you will have the address of the next instruction to be executed. Where you have stuck before you service your interrupt, you have stuck at 255th location. That means you have executed the instruction present at 255. After that, you have serviced an interrupt. So you have saved the address of 256. So you can come back to the location 256. You can start your program execution. Clear? This is your interrupt cycle. With this, your first unit is completed. And one more thing you should remember, here we are combining both CSE and IT, but the syllabus for IT and CSE is slightly different. Different in the sense, when compared to IT, CSE syllabus is very less. If we cover 4 units in CSE, according to CSE syllabus, 3 units will be covered in IT. That is the reason what we have planned is, we are planning to cover the syllabus according to the IT syllabus. According to IT, we will cover the syllabus first. That means we will cover 4 units. In CSE syllabus, as per CSE, we will cover 4 units. Once the 4 units were finished, we will split. IT and CSE branches will be shifted. So IT will be having a separate platform, separate timings. Similarly, CSE will be having a separate platform for COA. That is the reason. So what I am trying to do is, as this first unit is done, CSE people, you please go through your syllabus. So your first unit is done. After that, we are going to start the second part of your third unit. We are going to start the second part of your third unit. That is your computer arithmetic. Why? Because that computer arithmetic is included in the first unit for IT students. You don't worry, this and that. This first unit, when you jump to third unit directly, you may think that the sequence may be missed. There is no interconnection. That is the reason we are planning to go according to that sequence. After this first unit, maybe in the next class, I'll try to revise the first unit. After that, I will start the second part of your third unit, computer arithmetic. Is it clear? If you want, we'll share the screenshot. We will share the syllabus and in which sequence we are planning to taught, that I will share it in the WhatsApp. Any doubts in today's class? Okay, recording I'll send you. You please send your class group ID, I don't know whether all the sections have sent or not. Please send your class group IDs so that we will send you the recordings. The last recordings we have sent to IT section, CSE A, B, F. I think we have sent. Okay, recordings will send, PPTs also will send. Any doubts in today's class? Slides also I'll send, 529. I'll send the slides with 578. We'll send the recordings too. If you don't have any doubts, we'll start the quiz. You please share your group IDs in the WhatsApp group section group IDs. You please share in the WhatsApp group. Shall I start the quiz? Okay. Thank you. From next time onwards, please don't write anything on the screen, ma.